Good afternoon, Andy. Am I audible? Participants respond. Am I audible?
Yes, ma'am.
Okay, thank you. So today's topic 8051 serial communication. We have completed timers in the previous classes. This is serial communication. As we know, 8051 has what it has about serial communication. It has one UART, stands for universal, asynchronous, receiver, and transmitter. Right? One UART port is available in 8051, which do serial transmissions in asynchronous mode. Okay, you know the difference between synchronous and asynchronous communication. What is that? Synchronous and asynchronous communication. In synchronous, clock will be involved. Once both transmitter and receiver are agreed to a particular clock, then a bunch of bits in a serial form will be transmitted after synchronization pulses. The data rate will be high in this. But in asynchronous communication, there won't be any clock, but both sender and receiver will be agreed to a particular baud rate, number of bits transmitted per second. The baud rate here, actually, number of symbols transmitted per second. Here, our symbols are bits only, binary. So it is bit rate or baud rate. Both are same. In terms of character by character, they will transmit in asynchronous communication, which a frame in terms of frame means a start and a stop bits, including some parity bits, will be appended to actual your data bits that forms a frame, and it will be transmitted from transmitter to receiver. Here also same bit by bit only it transmits, but the disadvantage here, it has extra overhead bits, means actual data bits are surrounded by a start bit and stop bits and parity bit, okay, for assuring the communication. So these sometimes your start bit is one, sometimes a stop bit can be one and a half or two, and a single parity bit. Okay, so for every, if I suppose 8 data bits, for every 8 bits, extra two and a half or three or four extra bits, which we call it as a overhead bits, which doesn't actually provide the information. It is just extra overhead, which involves in the communication, that reduces the actual data bits transmitted per second. Okay, so that's why this is, we call it as somewhat slow communication when compared with synchronous. Okay, when compared with the parallel communication, serial communications are always slow because they transmit bit by bit. But in parallel communication, whole byte at a time it can transfer. Okay, so such a serial communication, one port is available in 8051. So let us uh, see what about that. So in 8051, to provide, to have this UART module, the circuit uses one buffer register, which is called S buffer, serial buffer register, to hold the data to be transmitted, and one control register called serial control register to control the data communication, and another register PCON, power control register, to control data rate, and two hardware pins. One is RxD, through which you can receive the data, and another TXD, transmit data pin, through which we can transmit the data bit by bit. These are actually the alternative functions of P3.0 and 3.1 to connect to the data network. Okay, so this is the communication circuit needed, the number of registers and hardware pins. So when I come for SBuffer is a byte register only, not a bit addressable, whose address is 99H. Okay, so actually speaking, it is a UART, full duplex universal asynchronous serial communication, right? So it's a full duplex, means through RHT data pin you can receive the data, and through TXD data pin you can transmit the data both parallelly. Okay, but we have actually a single register that holds the data, that is SBuffer. When we see physically, these are two registers inside the communication circuit. One is write-only register, which is used to hold the data to be transmitted out by the TXT pin. SBuffer holds the character to be written by the CPU. CPU will write the data onto SBuffer. That itself start the communication. Nothing but it starts framing the bits and sending the bit one by one through TXT pin. In that case, the SBuffer is working as only write. Okay, write-only register. Another register is read-only register that holds only the received data. Okay, whatever is the data that we have received from RHT pins, those bits continuously, one after one, it receives and it deframe the communication. Only the data bits are copied back to SBuffer. Okay, in that case, only read-only register is used. Okay, so this shows the diagram. Through internal data bus, the CPU will send the data on to SBuffer. So UART module will do framing and send the data through TXD pin. Okay. Through RxD pin, UART receiver module receive the data in a shift register. Once all the bits were received, 8 data bits from that shift register are copied back to SBuffer, which is a read-only register. And that will be read by the CPU via internal data bus. So this is the receiver end, and this is how transmitter functions. So to configure this communication, we have two control registers. One is a serial communication register, which is a bit addressable register with the address 98H. You can address the individual bits starting from the bit addresses 98H to 9FH. Okay. Coming to SCON register format. So there's the 7th data bit. So okay, so this one is the 7th data bit, SM0, SM1, SM2. Nothing but serial port mode specifier bits. SM0, SM1, SM2, serial port mode specifier bit, out of which SM0 and SM2 are defined to specify the mode of operation. SM0 is MSB bit. SM1 is the subsequent bit. Okay. 00 means mode 0. It is shift register mode. 01, it is mode 1, which is 8-bit UART mode. 10, mode 2, 9-bit UART mode. 11, mode 3, 9-bit UART mode. Okay. So serial communication. SCON register is used to configure the UART module in 4 different modes. Mode 0, Mode 1, Mode 2, Mode 3. Each with the definitions. Shift register, 8-bit UART, 9-bit UART, and 9-bit UART. Okay, out of these 4, only one mode is not UART mode, that is mode 0. It is a shift register mode. It is not related to UART. It means there won't be any framing kind of thing is happened in mode 0. It is just shift register mode. Whatever are the bits coming through S buffer, they will be shifted out one by one without framing. It is just shift register mode. So the baud rate that is used for this shift register mode is F oscillator by 12. Number of bits transmitted per second is F oscillator by 12. Next, for mode 1, it is 8-bit UART mode. The baud rate is a variable. You can configure at what baud rate the bits have to be transmitted out. Okay. Similarly, 9-bit UART with mode 2. Mode 2 is 9-bit UART with a fixed baud rate, which can be selected either by F oscillator by 32 or F oscillator by 64. Okay, it is fixed baud rate. Mode 3 is also 9-bit UART, but with variable baud rate. Okay, that's the difference between mode 2 and mode 3. Mode 1 is 8-bit UART. Mode 2, 9-bit UART with fixed baud rate. Mode 3, 9-bit UART with variable baud rate. Okay, we'll see what is the difference in these modes of operations one by one. And the next bit SM2, it is also second serial port mode specifier, but it is not defined in 8051, mainly used for multiprocessor communication. So this is not defined. You can just keep a dash or a 0 at this bit. And next bit is REN, which stands for receiver enable bit. Okay, receiver enable bit. As it is a full duplex communication, you can use a transmitter as well as a receiver. Okay, but your application, if you don't want receiver, then you can make this bit 0. That will disable the receiver module of your UART. Okay, so this REN bit is used to enable or disable the reception by using software. This particular bit can be set or clear by the user using software instruction like set bit REN or clear REN bit. Okay, by using this, you can enable or disable the receiver. And next, this is TB8, not TN, this is TB8. Okay, nothing but transmitted 8th bit. This is RB8, received 8th bit. Okay, so these two are valid only in 9-bit UART communication. In 8-bit UART communication, your data length is 8 bits. So S buffer will be sufficient to load your character, which is comprising of 8 bits. But when we come for mode 2 and mode 3, your data length is 9 bits. Okay, out of 9, least significant 8 bits will be copied in S buffer. That hold S buffer will hold least significant 8 bits, and the next bit, least significant 8 bits, nothing but 0 to 7. Okay, so bit 8 will be available in either TB8 during transmission and RB8 during reception. Okay, so these two will hold the 9th data bit indirectly. Okay, when I take from 1 to 9, if I take data bits as a LSB 0, 0 to 7 will be available in S buffer, and the 8th bit is available in TB8 and RB8 respectively, either transmission and reception. Right? That is about TB8 and RB8. Next bits, TI, RI. TI stands for Transmit Interrupt Flag. Transmit Interrupt Flag. So, like your timer overflow flag, whenever timer completes counting, it will set the flag indicating to the CPU that the time delay has been passed. Am I right? Similarly, during transmission, if the transmission is completed, then TI flag will be set by the module, by your UART module, indicating to the CPU that transmission is completed. Transmission of the previous character is completed. Okay, so that CPU can place the next character in S buffer that will proceed the communication of the subsequent character, right? As and when you load first character into S buffer, then UART module will take that 8 bits, add the start and stop bits, form a frame and start sending the data through TXD one by one bit. Okay. So likewise, to do this process, UART, obviously it will need some time. So before completion of the previous character transmission, your CPU should not write the next character onto S buffer. Due to this reason, CPU should know that the previous character transmission is completed. Okay. So that is indicated by the UART module to the CPU using the bit TI. Okay. Transmitter interrupt flag. Okay. Whenever you want to complete transmission of the previous bit, previous byte, then TI will be set. Okay. So if TI is set, it means it is an indicator to the CPU that the previous character is completed. So what CPU has to do? CPU has to place the next character in S buffer. Not only that, it has to be clear the transmitter interrupt flag. Okay. CPU has to clear the TI flag, then only the next character transmission will proceed. Okay. This is very important. CPU has to clear. It must be cleared by the software. Okay. CPU, in the sense, you need to write a software instruction for clearing the flag. Otherwise, transmitter will not proceed with the transmission of the previous character. Why this? We'll see. We'll see a bit. Remember this question. Why the user or the CPU has to clear the flag. The next flag is receive interrupt flag. Receive interrupt flag. Okay. So this is set by the hardware at the end of 8th bit in mode 0, halfway through the stop bit in other modes. Okay. So it is simple, understandable that whenever the reception completes, right? Whenever the reception completes, UART module will set this flag indicating that reception has been completed and a valid byte of data is available in S buffer to be read by the CPU. Okay, right? RI flag comes under receiver module. Whenever reception is completed, UART module will deframe and take the data 8 bits and places into S buffer and set the flag RI flag. Okay. So upon setting RI, CPU knows that a valid data bit is available. Valid data byte is available in S buffer to be read by it. Okay. So CPU will read the data byte from S buffer and stores and do whatever it wants. Okay. And then it clears the receive interrupt flag. Okay. It must be cleared by the CPU by using a software instruction like clear RE. Okay. So why these flags have to be cleared means we have single UART module by which a single signal will be generated by the CPU, by the module, which is an indicator to the CPU. Okay. So upon receiving a flag, transmitter interrupt flag means a transmission is completed. If TI is 1, transmitter is completed, UART has to copy the data. Okay. CPU has to copy next character into S buffer. Until it do, UART cannot proceed with the transmission. Okay. How UART knows that next data byte is ready upon observing the flag Ti. Okay, whenever Ti is cleared by the CPU, UART knows that S buffer is ready with a character. Then he can start transmission. Okay, so to avoid unwanted data transmission, Ti has to be cleared by the CPU. Okay, similarly, Ri. Upon receiving Ri1, CPU will read the data and it has to be cleared by the CPU back so that receiver will start receiving the valid data, next data. Okay. So if Ri is not cleared, right, if Ri is not cleared, then CPU should not receive the next data bit because S buffer is not at read by the CPU. It may be overwrite with the next received data item. To avoid that overwrite, Ri is a valid bit which will be cleared by the CPU. Then only the next data byte reception will start. That's the purpose of clearing by the CPU. Not only this, these two are ORed together and commonly will generate a single interrupt which has only single interrupt service routine, which we will be seeing in interrupt module. Okay, that is also another reason where the flags have to be cleared by the CPU. They are not auto clear flags. Okay, so that is about Ti and Ri. Okay, so with this it is clear that if Ti is equal to 1, it means what it indicates. If Ti is equal to 1 means transmission, we left with just 10 minutes, transmission of a character is completed. That means your S buffer is empty, so that CPU can write the next character. Okay, so if Ri is 1, which is set by the UART circuitry, indicating that reception is completed. It means your S buffer is full. Okay, it is ready with the character. So CPU has to read S buffer and it has to make the S buffer clear, free to receive the next byte. Here you need to load your S buffer with a new character, make it full so that you can transmit next byte. Okay, so that is the indication of Ti and Ri, right? So that's the register, serial control register, SM0, SM1, serial port mode specifiers with 4 different modes of operations, mode 0, mode 1, mode 2, mode 3, out of which 1 is shift register mode, remaining 3 are UART modes. And next SM2 not used in 8051, REN receiver enable bit, RB8, TB8, transmitter 8 bits, received 8 bits, Ti and Ri, transmitter interrupt flag, receiver interrupt flag. And next register PCON, power control register. Its value, address is 87H and it is not a bit addressable register, out of which only S mod, the most significant bit, is for serial communication. Remaining bits are not for that. These are actually CPU control bits, power control register. Next 3 bits are not implemented. And GF1 and GF0, these are general purpose user flag 1, general purpose user flag 0 bits. Okay. So apart from mathematical flags and some other flags like TF0, TF1, TI, RI, Okay, apart from mathematical flags like carry, overflow, we don't have zero, overflow, parity, auxiliary carry. Okay, 4 math flags, right? Apart from this, 3 user flags are available in 8051. One is F0 available in PSW register, and the other 2 general purpose user flags are available here in PCON register, GF1 and GF0. And next registers are next bits are PD, power down bit, and IDL bit. Okay, so power down bit, the oscillator will be stopped. Ideal bit, where the CPU activity will be stopped. Okay, so to make come out of either of these two state, you need to reset the CPU, or else you can even generate an interrupt to this CPU. That is about power control register. Now coming back to serial data transmitter modes in detail. The first mode, shift register mode. So it configures S buffer to receive or transmit 8 data bits using RxD pins for both the functions. Okay, see, for both the functions, you can either transmit or receive the data bits through RxD pins only. Okay, the pin TXD is used to supply the shift pulses. Okay, shift pulses, nothing but the clock pulses. Shift frequency, which is nothing but F oscillator by 12, is supplied through TXD pin. So during transmission, the data will be shifted out on every falling edge of the clock pulse. And during reception, your data will be shifted in on every rising edge of the clock pulses. Okay. So this is the shift register mode, just shifting out the data bits at a rate of F oscillator by 12. No framing, nothing is happened here. Through RxD pin only. TXD pin is used to supply the clock pulses. And it is very high speed serial communication we used to call, because if I take F oscillator operating at 12 megahertz, then the shift frequency is around 1 megahertz, nothing but 1 lakh bits. Not 1 lakh. 10 power 6. Nothing but 10 lakh bits are transmitted per second. That's why it is high speed serial communication. And next mode 1, which is 8-bit UART mode with variable baud rate. So your UART is used as a 10-bit full duplex receiver and transmitter that they receive and transmit the data at the same time. RxD is used to receive all the data. TXD pin is used to receive transmit all the data. And this is what I said framing. The first bit is always start bit, and remaining 8 bits are your data bits, and then 1 stop bits. Always start bit is low, stop bit is high. Okay. Once the framing is done, bits are shifted out from start bit onwards. First start bit, next data bit 0, and then data bit 1 likewise. So first start bit will be sent, after that bit 0, bit 1, bit 2 likewise till stop bits. It will be sent in this way, and the same way data is also received. Okay. Now, what is variable baud rate? At what baud rate, at what rate these bits are shifting out? Okay. So nothing but 1 bit duration will gives me actually the time interval for 1 bit to send out. Okay. Based on that value, you can have number of bits transmitted per second. Okay. This is the baud rate formula. So when I come for serial communication circuitry, you are already, when we come for timer circuitry, where your 8051 clock frequency is divided by 12 and it is given to timer circuitry, right? So when I come for serial communication, UART module further divide the clock frequency by 32. Okay. So your F oscillator is divided by 12 and it is given to timer. Okay. But the same F oscillator by 12, it is further divided by 32. So that gives me F oscillator by 12 into 32, which is given to your UART circuitry. Okay. And for UART, this F oscillator is a fixed frequency, which is 11.0592 megahertz. Why this is so? When I take 11.0592 megahertz, if it is divided by 12 and then 32, you take a calculator. We have just 1 minute left. Please rejoin again, all of you, to continue. So let us take your calculator with the value 11.0592 megahertz. Okay, divided by 12 and divided by 32. This into megahertz, right? 10 power 6. Okay, so this is the frequency of operating for UART 28800. So with this value, you can easily generate actual serial communication baud rate. When we go with any PuTTY or Teratum or any type of serial module, if you see what are the baud rates that these are supporting. When I go with